This is video 1.4 for AP Chemistry, all about electron configurations. The homework will be due Tuesday, August 26th at the beginning of class, as this will be what we'll be working on in class. So it's really important that you guys watch the video tonight here. It's a pretty standard formula you're going to be using through the next couple days here, and the quicker we learn it, the better. So your learning targets for us tonight are that we can determine the electron configuration for a given element. Up until this point, we've asked you guys to draw models of the atom for the first 18 elements, and that's no longer going to be enough. There's 118 elements on the periodic table, and we're going to be teaching you a system here that will allow you to do all 118 elements. So here we go. Alright, a little bit of review before we get into this. Guys, you already know that the protons determine the atom, the element it's going to be. And so 79 protons, for example, is going to be gold. Neutrons are going to be what determines the isotope, or whether it is an isotope of a given element. And so keep in the back of your mind, if we're talking about isotopes, we're going to be comparing two or more atoms and looking at the fact that they have the same number of protons, different number of neutrons, and it's that difference in neutrons that causes them to be isotopes of each other. And that leads us with electrons here. Electrons, you're going to be learning in the next few weeks here, are really responsible for the chemical behavior of an element. Why does it react the way it reacts? And so this lesson on electron configurations is going to start us down this pathway and introduce us to how electrons are organized. And it's this organization that really has a lot to do with how different elements behave. What I have here in the video is an example of an atom model, and that's of aluminum here. And if you did the math for it, we'd find it has 13 protons, 13 electrons, and 14 neutrons. And then to the right of the image there is the atom model itself with the protons and neutrons in the middle, 2 electrons in the first energy level, 8 in the second energy level, and 3 in the third energy level. This system becomes very cumbersome if you're doing more than 18 electrons. It's already cumbersome as is, going up to 18. And so we're going to use a method called electron configuration. Now, electron configuration takes the same information, but organizes it in a string of numbers, letters, and superscripts to place all the electrons in the energy level at the lowest possible energy, the ground state. So for aluminum, for example, if you look at the atom model, we see that in energy level 1 we have 2 electrons. Well, I can also represent that first energy level by writing 1s2, where the 1 indicates the energy level, the s is the suborbital, and I'll go over those here in a second, and then the 2 is the superscript, and that's the number of electrons in that suborbital. Now, every suborbital can only hold so many electrons. S, for example, or sphere, can only hold 2 electrons. P, or perpendicular, can hold 6. D, or diagonal, can hold 10. F, or function, can hold 14. And I'll go over these on the next few slides as to what order they get filled. But every energy level only has certain suborbitals available to it. Okay, so the first energy level only has an s suborbital, and so we got 2 electrons there. We're going to move out to that second energy level where I have 8 electrons drawn in that atom model there. But we don't have a suborbital for 8. Instead, we have a 2s2, and that's going to give me 2 of those 8 electrons, and then a 2p6, which is going to give me another 6. So if you add the 2 and the 6 together, you get 8 electrons in that second energy level. We're going to continue out to the third energy level where we have 3 electrons placed in our atom model, And so just like the model, we're in the third energy level. And so I'm going to write a 3. And then I'm going to write an S with a 2. And then a 3p1. Now, if you add this all up, we should get 13 electrons. Look at the top where it says 1s. Again, remember that can have 2 electrons in a s suborbital. P can have 6, D can have 10, and F can have 14. So if we start at 1s, what you do to use this chart is you start at 1s always, and if you have at least 2 electrons, you're going to fill that, and you're going to follow the arrows until you move around to the 2s. And if you have at least 2 electrons to a place, you'll follow that around to 2p and keep on going through the zigzag line, filling each suborbital and energy level as you go. As an example here of how this works, I've got 3 atoms that we're going to do. We're going to do beryllium, which I know has 4 electrons. Okay, so starting out with 1s, since I have at least 2 electrons to place, I'm going to place that 2 up there. And I still have 2 more to place, so I'm going to move around to the 2s. And I have 2 left to place, so that's going to be 2s2. So if you add the 2 up at the top here, the 1s2 and the 2s2, you get 4 electrons. If we look at boron, boron has 5 electrons, so we already know beryllium is 4, so I can write the same thing here. So boron's going to be 1s2 to give me 2. 2s2, that gives me 4, and then I have to continue around to 2p and place my last electron, which gives me 5. Carbon has 6 electrons. So it is 1s2, 2s2, 2p, and we're going to place 2 electrons because I have 2 to place there. On the next slide, I'm going to go ahead and I'm going to do a larger one so you could see how this order continues here. But remember, you're always going to start out 1s, and you're just going to keep going through the electron configuration until you have all the electrons for that atom placed. Here's an example of a larger element with 35 electrons. That's bromine, to show you how complex this electron configuration can become, but it's still way easier than drawing the atom models for each of these elements. Remember, you can do electron configurations for all 118 elements. You can do atom models for all 118 elements too. Just like in the previous examples, we're going to start at the lowest energy level possible, which is always going to be 1s. And since I have 35 electrons to place here, I'm going to keep going through this chart on the left-hand side until I get all 35 electrons placed. And so we're going to start out 1s2. That takes care of 2 of them. 2s2, there's 4 electrons total taken care of, and 2p6 brings us to 10 of the 35 electrons I need to take care of. We're then going to go around to 3s2, there's 12, 3p6, there's 18, and 4s2 brings me to 20 of the 35 electrons I need to place. Here's where this gets a little tricky. After 4s2, it's actually a slightly higher energy requirement to be in 3d than it is in 4s. So 3d comes after, and so that brings us to 30 electrons with 3d10. And then we're going to go back to 4p5 to bring us to 35 electrons. Tomorrow in class, you'll be doing lots and lots of practice doing electron configurations. You need to know this skill. It'll be extremely important for when we get into ionic and covalent compounds, as the electron configuration, and namely valence electrons, which you'll be learning about soon, determine the chemical behavior of the elements we're talking about.